Hello everyone. In this video we are going to talk about another phenomena that is observed in nonlinear systems, and that is called the limit cycle, which is a periodic behavior, a closed loop trajectory in the state space, in the phase space of the system, and it can be stable, unstable, or semi-stable. So the system that we're going to look at today is what we call the van der Pol oscillator, and I mentioned it in my previous video on double pendulum chaotic behavior. So the governing equation of this system is very simple. X double dot plus a nonlinear term, a damping nonlinear term, plus this basically restoring or spring term equals 0. So you can consider it like a mass spring damper system that has a nonlinear damper like this, where the damping is not just a constant mu times the velocity, it's also related to the position as well. So you have this nonlinear term. If this 1 minus x squared was not there, that would have been a simple mass spring damper system for which we know the exact solution, and it's a linear system. But this term here makes it nonlinear, and the person called van der Pol is the first person that discovered this behavior, this oscillation in these physical systems. And the system that he was working with was electrical circuits and vacuum tubes. And this is one such system, which is basically an RLC system. You see there is a capacitor, there is inductor, and there is resistor here with the voltage, and you also have a triad. So in this system, you can show that some kind of behavior like this, a governing equation like that, exists. And although the equation looks very simple, guess what? It does not have any exact analytic solution. Yet it has some interesting behavior. What is that? So if I draw x dot versus x in the system, so go to the phase or the state space, then if I start my initial condition anywhere, by the way, this oscillator that you see is the van der Pol oscillator with no exciting. So assuming that this guy could be 0, if this right hand side is non-zero, it's some f of t, then we call it a forced van der Pol oscillator. Okay, so here we are not going to talk about that. We're just going to talk about the van der Pol oscillator with no excitation. And that one also, the forced one, also shows a similar behavior, but here we're going to look at the one with no external excitation. So here, regardless of where I start my initial condition, so I can start here, for instance, at this point here, 1 and 0. Okay, I start here. If I start the system at x dot equals 0, x dot at 0 equals 0, and x at 0 equal 1, and select some number for mu that is bigger than 0, okay, let's say for instance 2, then what happens is, or 1, what happens is the system starts from here, and then what starts moving on this trajectory, and then you see it going, and then what happens is it falls onto this blue thick curve that is a closed curve, and any closed curve in the phase space means a periodic response, okay, because it repeats itself. Then it falls onto this blue curve, and what happens is this blue curve just keeps going on this blue curve forever. So I did not start on the blue curve in the beginning. My point was off the blue curve, but as time goes on to positive infinity, it doesn't need to, in this case just a little bit, I fall onto this kind of like a vortex, right? Like something that is grabbing me. It's like a black hole, basically. And then I'm absorbed to it, and I keep moving along it forever. Now, you might say, well, change your initial condition. Start from here, this point. That is like 2 and 0. Start from here, okay? If I start from here, that is like 2 and 0. Again, look. here I go on this small trajectory which is off the this blue curve, and then again I fall onto the blue curve, and then I go forever on that. So you see, it doesn't matter where inside this limit cycle, right, this closed-shaped curve I start, I go on a trajectory and ultimately I fall onto this limit cycle and I keep going. And that is the same if you start outside of it. So you might say, well, what happens if I start at 2.5 and 0, somewhere here? Doesn't matter. You're still gonna go on some trajectory that is kind of similar in shape but bigger than this limit cycle, and then what? Guess what? Again, you fall onto this and you keep going. So this is an attractive, or you might call a stable limit cycle, that whether you start inside of it or outside of it, after a little bit time passed, you fall onto it and then you keep doing that periodic behavior forever. Okay, so that is called the stable limit cycle. And this van der Pol oscillator does have such response, which is very interesting. Now, the shape of this limit cycle does depend on this parameter mu. So if mu is entirely 0, what happens? If mu is 0, then this term will go away altogether, and you're down to what? The x double dot plus x equals 0, which is basically the simple harmonic response. In this case, you're in the phase space, you're going to look at the circle, right? The response of the harmonic response in the phase space is going to be a circle, which is what you can see over here. This is for mu of 0. And as mu gets bigger than 0, mu is increasing, the shape of the limit cycle is changing, and as mu gets bigger and bigger, it kind of gets more distorted. Okay? So it gets like this, but for smaller mu, it is kind of more square shape, or the axes are, the size of the deviations are similar, but as mu gets bigger along the x dot, you get basically bigger distortions of the circle. Right? So, and I'll show you all of that in my MATLAB code, but the shape of the limit cycle does depend on the mu. So, as I said, the limit cycle could be stable, like what we have in this van der Pol oscillator, but there are two other scenarios for this limit cycle. The other scenario is it could be unstable. What is that? Or a repelling limit cycle. In this case, instead of this, let me draw a shape for you. So let's go and look at another shape. If I have the same shape, okay, something like this. If I have this shape and the limit cycle is unstable, if I start very close to it here and I look at the basically the trajectory, instead of getting closer to this, it gets further away from it. Okay, so it's like a spiral but outward. And if you start inside of it, then instead of going closer to it, you get what? You get further and further away from it. So you get an inward spiral. Okay, so that is an unstable limit cycle. And there are scenarios where, depending on where you start, inside of it, you might get away from it, but outside of it, you can converge to it. This is called a semi-stable. On one side, it is attracting the trajectories. On the other side, it's repelling it. Okay, that is what we call a semi-stable. So your van der Pol oscillator has the stable one. Inside or outside doesn't matter, it will attract you. But these other ones, no. Now, before I go and show you my MATLAB code, I want to mention something, and my goal was not really to go into a lot of details, because if you want to study limit cycles, that's several lectures of its own. Just want to mention that there is something called, in linear dynamics, called Levinson-Smith Theorem, which guarantees for systems with governing equations like this van der Pol oscillator, and a little bit more general than that, which we call a Leonard equation, and it's any equation of this format. It says if the governing equation of the system is something like this, where this f and g could be any function, and this f and g have some specific conditions, then I guarantee that the system has a non-zero closed trajectory, a limit cycle, which is stable around the origin. So we want to see if this theorem is applied and is applicable to this van der Pol oscillator equation. If it is, then this theorem says yes, there is a limit cycle and it's stable around the origin. And by a single simulation, you can see the shape of it. So in this case, this is one of the functions, this is the other function, right? So one of them is negative mu times 1 minus x squared. Let's write it down. And g is just x. So in this case, let's see if f and g have the other required condition, because the format of van der Pol is a linear equation, but does it have the other conditions, 1, 2, 3, 4? If it does, then this theorem says you do have a limit cycle. Okay, let's take a look. First thing says f of x should be an even function and continuous. In this case, it is. You see, it's 1 minus x squared. It's all the even powers. So it is the case. G, which is this one, is an odd function. Of course it is. And if x is bigger than 0, then g of x, which is the same as x, in this case, is bigger than 0. And it's all continuous too. So both f and g are continuous. G is odd, f is even, and g is positive for positive x's. So first two conditions are satisfied. Then it says if you calculate the integral of g of x from 0 to y and call it g of y, that function g of y should go to infinity if y goes to infinity. Well, let's integrate. So here we integrate from 0 to y of g, which is x dx. And so if we call it g of y, clearly this is going to be y squared over 2, right? And does this function go to infinity when y goes to infinity? Of course it does. So this condition is also satisfied. Then what? It says if you call the integral from 0 to y of f of x dx now f of y, that f of y should have some properties too. What are they? So first let's calculate it. So in this case, f of y is integral from 0 to y of this other function, negative mu times 1 minus x squared dx. And if we do that, that negative mu can be brought out. So it's going to be negative mu times y, right? And then you have positive mu x squared. So it's going to be positive mu over 3x cubed. And so that's going to be y cubed. Okay, so this is f of y. Now, what conditions does this f of y need? So let me bring it up here so we can look at it together. Okay, so that was f of y, and this guy was g of y. I just put them up there so we can study them. So it says, first of all, f of y should go to infinity as y goes to infinity. Of course it does. You can see that. The other thing is, for some number k bigger than 0, you should have this fy be negative. And then, for the range y between 0 to k. And then, for y after k to positive infinity, this function should be positive. So on some side of parameter y, as y goes from 0 to infinity, from 0 to k, it should be negative, and then as it goes from k to infinity, it should be positive. Well, is that the case? Well, if we plot this function, f of y versus y, right? So at 0, it's 0. At 1, it is negative mu, positive mu over 3, so it's negative 2 mu over 3, right? it's here, and then let's make sure I did it right. Yeah, then if you say 2, then this is like 8 over 3 minus 1 over 3, right? So it's going to be positive 5 over 3. 2. And so you see, it's kind of like this. Okay, it's a cubic function. There is some range that this f of y is negative, and there is the other range where f of y is what? Positive. So this intersection point is your k parameter. So you see your function has all the required things, and for that reason this theorem says there is a limit cycle for your van der Pol oscillator equation. And we saw that actually there is. Now let me show you my MATLAB code. So here is my MATLAB code. Again, I used ODE45 here, and in this case it's very simple because you only have 2 state variables, x and x dot, which I call here z dot 1, z and z1 and z2. And the way I wrote this function is it can accept parameter mu as an external parameter. So you can pass to it mu in addition to t and z. So what I did first, I ran this function 3 times for 3 different initial conditions. One is this point, which is almost at the limit cycle for mu of 1. Then for the same mu of 1, one time I used a point inside the limit cycle, 1 and 0. The other one, I ran it for a point outside the limit cycle. And I show you that these 2 curves will converge to this one here. Okay? The other thing I did is, for this case, for the case of limit cycle, I plotted x versus time instead of plotting x versus x dot versus x, which is the state space. And I did it for this figure 1. In figure 2, I plotted x versus t, so you see the behavior is actually what? Periodic. And in figure 3, I changed mu every time from 0 to 4, just like this picture. So it goes from 0, which is a circle, all the way to 4, and I want to regenerate this shape for you, this picture. So here you see I change my mu every time I pass that mu, and the initial condition for all of them I started at 2 and 0. And the reason is you can see that these all different limit cycles and all these different points, these curves, they all kind of share this point here, which is basically like 2 and 0. So I use that point, or you can use negative 2 and 0. And then I plotted all of these different solutions on the same curve, and I showed their mu's, and I use a random color for all 9 different curves. Okay, so let's go ahead and run. There we go. So this is that shape regenerated for you. The effect of mu on the shape of the limit cycle, as you can see here, this is with mu of 0. And as you go to mu of 4, which is all the way here, the distortion gets bigger and bigger. So I regenerated that picture. This is that periodic response for mu of 1. As you can see, the system x versus t absolutely behaves harmonic and predictable. And this is the other plot, as I said. This blue curve is your limit cycle. This black one is the trajectory outside the limit cycle converging to it. And the red one is what? The trajectory starting inside the limit cycle and converging to it. Okay, so if you want, I can add some legend to this figure 1. There we go. So you see now, I showed you these this extra legend here, and you can put this outside, or in this case, maybe I can put it best. Maybe best can leave it inside and keep the size of the picture and doesn't shrink it. Let's see, there we go. Yeah, it's better actually. You can probably bring it here toward the center or put it here on the northwest too. And you clearly can see that you will go to the stable limit cycle, and this is for mu of 1. So hopefully you learned a little bit about this phenomenon, this stable periodic response of the some nonlinear systems, and this van der Pol oscillator is not the only system that shows a limit cycle. There are many nonlinear systems that have a similar response, so I just wanted you to know about it. This picture, this one, and most of this text, as I mentioned over here, are from Wikipedia, although I could regenerate them in MATLAB for you. But I just wanted you to know that most of this material are coming from Wikipedia, and I don't claim any ownership to anything. So hopefully it was useful to you. I'll see you in the next video. Thank you.